Hi everyone, welcome back to Dr. Tutor. Today we're going to keep going on with Unit 3 of QCE Chemistry, and we're going to do Brønsted-Lowry acids and bases. So the main premise of the Brønsted-Lowry model is the idea that acids donate protons, which we kind of discussed earlier, and remember protons is the same as hydrogen ions, and that bases accept those donated protons or hydrogen ions. So that is how, in the Brønsted-Lowry model, we define what is an acid and what is a base. It depends whether they donate or they accept, and you can kind of remember because acids donate. And if we write out some example equations for this, right, we can have a look at this one. So let's say we have HCl plus H2O, which is liquid, and that goes to Cl minus, which is aqueous, and H3O plus, which again, this is the same as H plus or P plus. That would be our balanced equation. What we can see happening here is our acid, this is our acid, right? And it donates this proton to the water, right? So it is donating this H to the H2O. So in this case, this is the base because it's accepting that H, right? And then what we see at the end is that, yeah, it's accepted that extra hydrogen, and that's why it has 3 now, right? So just a note here, we use this arrow because HCl is a strong acid. That's why we use that arrow instead of the equilibrium one. And another note is something which I'll come back to in a second, but we call this the conjugate base equation. Let's do another practice equation for bases. So let's say we have NH3, which is a gas, plus H2O, which is our liquid. And this is a weak base, so we're going to use the equilibrium arrow. And then we get NH4 plus aqueous, and OH minus, also aqueous. Okay, now in this case, we can see that this H is getting donated to here. So that makes this the acid, because it's donating, and that makes this one the base, because it's accepting, okay? And like we can confirm that by looking here, we can see that we've got an extra H over here. So this is the one that has accepted, and this is the one that has donated. So this is basically the water, but it's lost that H that it donated, and this is the base, but it's gained the H that the acid donated to it. So now in this case, we would call this the conjugate acid. Now what is this conjugate nonsense that I am yapping about? Well, let me tell you in a moment. I will come back to it, I swear. Okay, so one more thing that you need to know first, though, is there's something called amphiprotic. So amphiprotic species, and remember species in chem just means like a molecule, basically, that's all it means. So amphiprotic species, amphi is like amphibious, you know, amphibious animals are in water and in land, like they do both. So amphi kind of means both, and again, remember protic means like P+. So amphiprotic species, maybe you can guess this, they both donate and accept, okay? So they're kind of like acids and bases, and that is, for example, that would include water, as we've seen here. In this equation, it acts as a base, but in this one, it acts as an acid. And that's specifically, like, according to the Brønsted-Lowry definition. So the main example would probably be water. Another example is this, which is HCO3-, and amino acids. They're all amphiprotic species. Amino acids you'll come back to in, like, Unit 4. This one, I think I have an example relating to this at the end of this video. But it's not, like, you don't really need to memorize it or anything. Alright, so what is this conjugate stuff? Let me tell you. So when we are talking about these reactions, right, we would usually represent them in an equilibrium situation. And so since it's an equilibrium reaction, we have this happening and we have this happening. I know I have said that many times. But what that basically means is that when you have the reverse reaction happening, one of these has to be an acid and one of them also has to be a base, because you're doing a swap C of the H that you donated. So this donated it before, but now, if we're going to do a take-C back-Cs, then this becomes the donator and this becomes the acceptor. And so that's what this idea of conjugate acid or conjugate base means, is that when you're doing the reverse reaction, this is now the fake acid and this is like the fake base. And so the official name for that is conjugate acid or conjugate base. So this would be our conjugate base. And that just means that when the reverse reaction is happening, this is the one that is accepting and this is the one that is donating. So like, for example, this H is going over to here. What we say is that these are conjugate acid-base pairs. So, like, this base is, like, to this conjugate acid, and this acid is to this conjugate base. Like, the official way that we can think of this is that you'll always have an equation where it's, like, acid plus base will be in equilibrium with a conjugate acid and a conjugate base, as shown in this example. All right, so then what this conjugate stuff is actually important for is to understand something called buffers, which you may have heard of before, but buffers are basically solutions that resist change in pH. That's the main definition, that's the main thing you need to know. Resist change in pH, okay? And what they actually are, the way it describes them in the syllabus is conjugate in nature, which basically means that they usually have a weak acid and its conjugate base, or they have a weak base and its conjugate acid. And the reason why that's important is because in this equilibrium setup where we have these conjugate pairs, right, what happens is, since it's an equilibrium system, Le Châtelier's principle applies. And since Le Châtelier's principle applies, when we have changes in pH, this conjugate buffer system will oppose that change, and that's why it can resist the changes in pH, okay? Let's take an example, which is human blood, which is kind of a weird example, but it's very interesting, so that's why I'm bringing it up. It also relates to this, oh my god. It also relates to this that we talked about before. So let's kind of see how this works. So the normal equilibrium for human blood, and I'm going to write this in pink for funsies, is CO2 gas, right? We have some carbon dioxide in our blood, and H2O liquid, and then that is in equilibrium with H2CO3, which is aqueous. This is not totally accurate, but just for the sake of understanding. You don't need to memorize this equation or anything. And then plus H plus, aqueous, okay? So you can see that here we have a bit of an acidic solution, and that's fine, your blood can be a bit acidic sometimes, it's okay. But that's the whole point, is that if it gets too acidic, right, then you'll favor this reaction as opposed to this one in order to prevent it from getting too acidic, okay? And similarly, if you have too much carbon dioxide in your blood, then it can favor this to get rid of the extra carbon dioxide, right? So that's how we stay alive. So specifically, when we add OH, all right, if we increase the OH minus concentration, then what will happen is you get this reaction happening. So OH minus, aqueous, of course, plus the H2CO3. That should probably be in there, but anyway. You favor this way, and you don't really favor this way. Or the better way to draw that would be like this. And then you have this other stuff on this side, which is the same as this. And what's happening here is basically this is one of the ways that this can act as an amphiprotic species, because in this situation, it'll make more sense when I show you the other one, but in this situation, what it's doing is this guy here is accepting a H+, right? That's why it's turning into this. And this one is giving it away. So we're giving away this H to this one, and then if we're doing the reverse reaction, then this one is giving away the H to this one. And so what that means is that this is our base, this is our acid, and then this is our conjugate base, and this is our conjugate acid. Okay, so we can see that for this setup, this one could be acting as a base, right? If it's doing the reverse reaction, then it's acting as a Brønsted-Lowry base. Alright, let's take another example. If we increase the H+ concentration in the human blood, then the reaction that we'll get is this. So, hydronium. I'm going to stop writing the SATE symbols again. Sorry, chemistry teachers. I know that you do not like me for this, but sorry. And then on the other side, we'll have this happening. So again, let's figure out what's the base, what's the acid. So in this case, this one is getting donated to this, right? Because we're going from 3 H's to 2 H's, and then from 1 H to 2 H's. So we know that this is the donator, this is the acceptor. And then on this side, we know that this is the donator, and this is the acceptor, okay? Or we can say then, this is the acid, this is the base, and this is the conjugate acid, and this is the conjugate base. Okay, so the key takeaways and the reason why I've showed you all of this is basically just to demonstrate some examples of how to choose which one's the acid and which one's the base, right? So you just have a look at the equation, see which one is donating, which one is accepting, and the one that's donating will be the acid, the one that's accepting will be the base, and then have a look at the other side, flip the reaction around in your head, and have a look, see which one would donate it in the reverse reaction and which one would accept it in the reverse reaction, and then that's your conjugate acid and your conjugate base. The other way that you can think about it as well is that the conjugate base is the one that has already donated, and so it's not going to donate anymore. And the conjugate acid is the one that has already received, so now it has stuff to donate, right? That being said, think about it whichever way you want, whatever's easiest for you, but that's just how I like to think of it. The other thing that's important to keep in mind is that when you're talking about a buffer solution, you can use LCP to predict how it will respond to changes, right? So if you have a balanced equation, you can use your normal Le Chatelier's principle stuff to figure out which direction it's going to favor, depending if you increase the concentration of H plus or the concentration of OH minus, because you just apply your normal LCP concentration related rules. And yeah, that's pretty much it for Brønsted-Lowry acids and bases. I hope you have enjoyed this video. Please comment if you have any questions, and don't forget to like and subscribe and send this video to your friends if you enjoyed it. And if you want a full subject guide, then you can see the link in the description and you'll be able to find online tutoring, assignment help, and a brand new program called Active ATAR, which if you become a member, you get access to all of our educational content for all subjects and literally thousands of practice questions with explanations and answers. So go check that out. Thanks for watching. Bye.